Okay. Hello. Good, there's energy, even though it's this early. So as you can see on the slide, my name is Daniel Moth, and I'd like to welcome you to this session on C++ AMP. C++ Accelerated Massive Parallelism. What a great name that is, huh? So those of you that may have seen some of my online content over the past years, or maybe caught a presentation at another conference, will know that I've been focusing on .NET previously. So I've been doing .NET since 2000, in fact. And now, with the whole C++ renaissance that's happening, and with cool technologies like C++ AMP, I'm testing the C++ waters. So I thought I'd share that with you, because I'm sure that some of you will be .NET developers that are interested in tapping into the power of the GPU for compute purposes. And you may be thinking, hey, this is going to be a bit scary. Don't worry, you're in good company. I had to go through this recently, and it's easy. It just works. Also, for the experienced C++ developers in the room, you may be thinking, yeah, working with GPU for computation, that's got to be hard. Again, if I can do it, an untraditional C++ developer, then you definitely will be able to. So it's all going to be very, very easy. And on that front, I wanted to check the experience that I'm assuming here. So let's see, how many people in here have been programming with C++ for, let's say, over 5 years? Can I have a show of hands? That's the majority. How about 10 years? Still a few. 15? Oh, most hands have gone down. Now, how about more? This is the big one. More than 20 years. That's very few hands. And one of the hands that's up is Kate Gregory. And Kate Gregory obviously has been programming for over 20 years in C++, and she's been an MVP for a long time. And when she heard about C++ AMP, she was very excited about the technology. And she got in touch about, hey, I'd like to play with this, maybe write a book and so on. And we said, yeah, sure. And she's actually managed this week to put online, when did you post it? Was it today on? So this morning or last night, something like that, she's put on her blog a digital version, a free version of the first 1 or 2 chapters. And for you in the room, she actually has hard copies for you to collect at the end of the session. How cool is Kate? So thanks, Kate. Double thanks from me, because you caused an applause at the beginning of the session, and you've given an incentive to everyone to stay until the end. So that's great. Thanks. So how are we going to spend this session? So here's my agenda, and I'm going to work backwards. So at the very end, I'm going to summarize what you've seen, and I'm going to give you some links to where you can go and find more content, because we already have a lot of content online. Before I get to the summary, I'm going to show you a demo of the debugging experience. So this has not been shown outside of Microsoft previously anywhere. So at the very end, you're going to be able to see that. So that's another reason for you to stay until the end. Before that debugger demo, we have the main section, which is what I've named up there code, which is the biggest section of this session, which is basically code on slides explaining the API. And before that is where we are now, which is setting the context for the session. And one way to get a context of what C++ AMP can do for you is to actually look at running applications, look at samples. And if you go out in the expo area, you'll find our hardware partners there. So you can go and look at AMD's booth and NVIDIA's booth, and you can go and see a C++ app running on their hardware. And you can talk to them about how excited they are about C++ AMP entering this space. But you don't have to go all the way there right now. You can go after the session. Right now, I can actually show you a demo right here. So let's go and switch that machine, and that machine, and that machine. So after a 3-button click, we should get this machine, which is timed out. There's a Windows security in action. And what I have in here is the N-body demo. And I've shown this previously at other conferences, so if you've seen it, well, you're going to see it again. So what do we have here? We have a simulation of these bodies, these particles, in terms of how they interact with each other in a gravitational way. And you can see what's happening up there, and you can see how many bodies we have. You can see how many bodies we have either by counting the dots on the screen, or by actually looking up here where you can see it says bodies, 4,096. And also up there, you can see the frames per second we're getting in the gigaflops that we're getting at this point out of the CPU. So this is running serially on the CPU. What I can do is I can throw more bodies at this. So if I was to go here and just up the number of bodies, let's say 5,000, you would see that we haven't really dialed the gigaflops up, and the frames per second have gone down. What this is telling you is that you've maxed out the power of the CPU in a serial manner at this stage. You're not going to get any more out of it. So you need to find alternative solutions if you want to get better performance or throw more data at the problem. So what I can do is I can actually go and switch to a multi-core solution. So now I'm going via a different code path. I'm using the Parallel Patterns Library, PPL, that we released in the last cycle. And you can see the frames per second have gone up, and we're getting more gigaflops out of the hardware. So we're fully utilizing the CPU at this point. I could throw more bodies at it, but you're not going to see really much of an improvement. In fact, you can see that it's staggering a bit, and now the gigaflops, that's about where they max out. So at this point, if you have more data to process or you want to get better performance, you're not going to do that on the CPU with this implementation. So what can you do? Well, what you can do is you can actually take advantage of the GPU. So what I've done is I've coded another code path here where you can go and offload this computation onto the GPU. So if we go and switch here to a C++ AMP implementation, that's what happens. So, of course, we're now getting 300 frames per second. We're getting 600 and something gigaflops out of this thing. And we can go and throw more bodies at it. That's the beauty. So I can throw more bodies, and you can see that it's still very fast. The gigaflops just keep going up because we can throw more data at the problem. I could go even further up, and you get the idea. Of course, this remains responsive, so I can go and zoom in, zoom out, rotate it, and all kinds of stuff. And the GPU is doing that for us. So what you're seeing is that when you have an algorithm which is data parallel in nature, because that's what we have here, when we calculate the position of each body with regards to every other, it's a data parallel operation. You're doing the same instructions. The only thing that changes is the data, which is the body in this instance. So when you have such an algorithm, you can actually offload it to the GPU, which is much better at executing data parallel algorithms. It's much faster, and this is the result that you get. You can throw more at the problem. Now, before I go back to the slides, I think you get the point as to what the GPU can do for you. In this box back here where I have this GPU, I have another GPU in it. I have a second one. So the one that's running right now is an AMD one, and the other one is an NVIDIA one. So I have from the two hardware vendors, two different cards. So what I can do at this stage is I can go and say, I want to use both of them. What do you think is going to happen then? And you have to think about this a bit. When you introduce second GPU, it's not just all automatic, more power. You also have more overhead because you have to copy data across and back to the CPU. And so there's more overhead. But if I go and switch to the multi-GPU solution, you'll see that we are getting more gigaflops, and I can keep throwing bodies at the problem. In fact, you know what? I'm just going to go all the way. So if we go all the way here, it's obviously now struggling itself. You go like 7, 8 frames per second. But look at the gigaflops. We're getting over a teraflop from just a desktop machine that I've got back here by actually using both of the GPUs. All right, so at this point, we'll go back to the slides. So what do you think? Does that kind of express the kind of power we're talking about here? All right, so there are other examples. This is just one example that I've shown you, but here is a slide from NVIDIA that shows the kind of numbers that their customers are seeing by taking advantage of heterogeneous computing. So basically, the speedups that you're seeing here, for example, 149 times faster, is comparing a solution that was using only the CPU with a heterogeneous solution that was also using the GPU. And you can see there's various domains, and when you get the slides, you'll be able to read more about them. I'm not going to go into each one. So why is this happening? And to see why is this happening, why there is all this performance for you to get, you can actually compare the CPU and GPU together. And you can see, those of you that can see the images, so that's an AMD CPU and an AMD GPU. And just by looking at the silicon, you can kind of tell what the difference is. Fundamentally, what you have on the GPU is a whole bunch more cores. On the CPU, you have a lot of complex silicon. It's more like, I think of it as a jack of all trades, right? So the CPU can do a whole bunch of stuff. Your CPU threads can do a whole bunch of stuff. But your GPU side can do one thing, data parallelism, but it can do it very, very well. So one way to think about it is that you have so many more threads on the GPU, but they're not as smart. They can't do everything. But they're very good at what they're doing, which is number crunching. So you can think of the GPU as a number cruncher. So I'm not going to go through all the points that I have up here on the slide. As a developer, the simplified view of looking at this is I'm still going to have a CPU application. And somewhere in there, I'm going to have some algorithms, in other words, some functions that are doing a data parallel operation. So it's the same instruction that I want to do on a large set of data, maybe multidimensional data. And that algorithm, that function, I'm going to offload to an accelerator such as the GPU so it can do it a lot faster, and then I'm going to get the results back to deal with them, whether it's getting the results to put them on the screen or getting the results to then go and do further processing. So that's really what we're talking about. And when you think about that scenario, you may be thinking, OK, that's great. So what's the problem today? What are you trying to address? Well, today, if you try and do this, you're going to end up using an exotic programming language, like a different compiler, a different language, different syntax, different tool chain, for what is essentially very small parts of your program. So you program your CPU application in a mainstream language like C++, and then you've got to go and acquire different tools and different skills in order to do a small part of your application to offload to the GPU. And if we leave it like that, it's never going to become mainstream, and all this power will remain untapped. And that's what C++ AMP is entering this space to deliver, a mainstream solution in C++. So that is the situation today, and that's what I'm going to focus on. But I just wanted to let you know that there is another issue, which is this space is really in motion. So all hardware vendors are changing what they're doing. The CPU and the GPU are coming closer. So this is a picture of AMD's APU, where they've taken the CPU and GPU and put them together on the same die. And they're coming closer, not just physically, but also in the capabilities. So you're seeing the GPUs getting more capabilities of what the CPU can do, and you can see the CPU getting more capabilities like the GPU. So the hardware space is definitely in motion, and Microsoft is uniquely positioned with all the close partnerships that we have with all the hardware vendors to actually know what the hardware vendors are thinking, and we're able to design a solution that is future-proof. So we're able to design a solution that addresses the need today for GPU, for general purpose GPU computing, but also that is future-proof for hardware that we've yet to see. So that is a bit of background about why we're entering the space and what C++ aims to fill the gap of. But what is it? So C++ is part of the Visual C++ compiler. So this is the same compiler that you use for your CPU, the same compiler you use for the GPU. It's the same language that you know. It's the same compiler that you have. It has tight integration with Visual Studio. So you only need to learn one IDE. You have one experience for all of your needs. And what C++ AMP is it's a key language new feature that I'm going to show you later. But fundamentally, it's a library. So it's an STL-like library. So we're taking advantage of templates heavily. And it's a library that allows you to express your data parallel algorithms. So it lets you deal with large data, potentially multidimensional data. And it lets you do that and express that in a manner that exposes parallelization that can be offloaded to heterogeneous hardware. And what we're doing with C++ AMP is we're building on top of DirectX. So we're building on DirectX, and that's a great thing because it's ubiquitous, like it's everywhere on every single Windows box, and it's robust. Through the rigorous Windows certification process, it's a robust platform to build on. I have to note the DirectX and Direct3D aspect of things are not exposed anywhere in our core API. So I'm telling you this, but if I didn't, you wouldn't have to know, essentially. So when you look at these things, this metadata about C++ AMP, it is obviously what its benefits are. So performance. It allows you to offload your data parallel algorithms to the GPU and get the kind of performance that I showed you earlier. It is productivity. You get to reuse your existing skills and assets directly to take advantage of this new paradigm. And hardware portability. The hardware portability that we have is second to none in the industry. What I showed you earlier was a single binary executing and at the same time taking advantage of two hardware vendors' cards. Nobody else can claim that today. Nobody. So those are the advantages of C++ AMP. And at this point, we're kind of done with the context, and I'm about to move to code because I'm sure you're all thinking, yes, I want to see how you work with this. But before I do that, are there any questions at this meta level that are burning in your head and you want to ask? Yes? So the question is, you're building on Direct3D. Can this run on something else except Direct3D? I'm going to cover that later, but in a nutshell, we could change our implementation at any point in the future, and we're going to make the specification open, and we're working with other compiler vendors so they can implement it in their compilers and on other platforms, and they can build on whatever they like. Yes? Is there a minimum requirement of Direct3D, like which version of DirectX you support? Is there a minimum requirement of Direct3D? Yes, there is. It's DirectX 11. So as long as you have hardware with a DX11 driver, you're good to go. Not 11.1, but 11? Correct, 11. With 11.1, there's certain advantages that you'll know from DirectX 11, so we expose those as well. Yes? Do we support OpenCL? Since we build on Direct3D, our implementation doesn't. But another compiler vendor is free to take C++ AMP and build it on top of OpenCL, because the OpenCL is at that level. I'll take one more. Oh, that scared you. So there isn't one more. Great. So that was the context. Let's go and have a look at the code. So here I have the simplest code I could write. So here I'm adding two arrays together. And if you look at this, it's a data parallel algorithm. Why? Because they're in the loop. What I'm doing is independent of all other loops, and it's basically doing exactly the same thing. The only thing that changes is the indexing into the data. Hence, what I'm doing is I'm changing the operation on different data. But I could run this on multiple threads, and it would all be fine. So assuming I have a large set of data, I could take this and offload it to the GPU. So how do we do that? Well, let me go and insert some spaces and copy this code to the other side. I've just done that. And now what we're going to do is we're going to take one side, and we're going to make it use C++ AMP in order for it to be able to run on the GPU. So keep an eye on that. That's it. So what I want to point out here is there's no other hidden code anywhere. Like, this is the entire code. There's no some setup code that I'm hiding somewhere else. I haven't had to change any compiler switches. This is the same compilation that you would do today. There's no environment variable settings, nothing. All I did is included amp.h, which is the header file that you can use the library. I'm using the concurrency namespace just to save me some typing further down. And that is the only change I do in my program. Recompile, run. Now it's running on the GPU. That's how minimal the API is. Now let's zoom in on this function with the C++ AMP and have a better look at it. So the first thing I want to draw your attention to is the entry point, parallel for each. So that is the entry point in the C++ AMP. There's already a parallel for each in VS 2010 with the PPL, the parallel patterns library. So this is just another overload in our header file. So parallel for each is where you go and say, hey, I want to give you a lambda, that's a second argument, and I want you to execute that on the GPU. And with the first argument, the parallel for each, you're saying, and I want this many threads. Because when you program the GPU, unlike on the CPU case, you decide exactly how many threads you want to have executing your code. And they're very lightweight, so you don't have to worry about context switching and stuff like that. So you say as many threads as you want. So typically, you'd schedule thousands of threads, maybe 1 million threads. That's how you should be thinking about this. It's a massive parallelism. So you told it how many threads, and then if you look at the lambda itself, this is our key new language feature, restrict direct3d, which you can put on functions and lambdas. And that basically instructs the compiler to check, can this code execute on the GPU? Because there's some restrictions in what you can do. Remember at the start I said those GPU threads can't do everything. So the code you write to execute on the GPU cannot do everything. And I'm going to talk about what the restrictions are. But this is how you'll find at compile time if you're doing something wrong. The other thing to notice in the lambda is that it takes an index. And the index, you can think of that as the thread ID. So what do we have so far? You've called parallel for each. You told it in the first argument how many threads you want to schedule here. Then you give it a lambda that's going to be executed once for each thread that you actually specified. And in that lambda, you're going to receive an index, which is going to be different every time. And then you can write your code. So what are you going to do with that index? Well, this is about data parallelism, right? So what you're going to do with that index is operate on some data. And the data, you don't explicitly pass into the parallel for each. Instead, because we're using this nice lambda syntax, that's one of the benefits, you can capture the variables of your data into the lambda. And the way I'm doing this here is you cannot operate on the data that you have on the CPU directly. So you wrap that in an array view, which is one of our types, and then you capture that in there, and you do the operation. I want to point out that if this was a two-dimensional addition I was doing, so it was like a matrix instead of an array, what I would change is these ones you see here, and over here, all these 4 ones, they would change to 2. And of course, when I create the array view, I'd have to pass what the other size is. And everything else would stay the same. So it's great at working with multidimensional data. So the rest of this session is going to be about drilling further into these things to really understand them, because I've just scratched the surface here, and also introduce other concepts and other types that we have so you can understand the full gamut of the API. Again, before I move forward, are there any pressing questions after you've just seen this? Yes?
It appears that this add arrays method is synchronous in that it's going to complete all operations, loading the data in, retrieving
Right.
the data back before completing. Is there mechanisms for making asynchronous?
So the question is about synchronicity and asynchronicity. There was a false assumption that this is synchronous. I'm going to cover that as we move forward. Yes?
Does the restrict directory give you runtime protection against people that don't meet the requirements, or do you have to ensure that elsewhere?
The question is around restrict directory, which I'm going to go into further later, but just to answer your question now, it's a compile time check-in. And I can take one more. Yeah, that trick works every time. OK, so now let's go and look at some of these types. And this is going to be very simple, I think you'll find. So first I want to talk about three types: grid, extent, and index. Index represents an n-dimensional point. It's a point, and you can say for how many dimensions. That's fairly simple. Extent, which you can also think as, whenever I say extent, I think size, is a number of units. So it defines the n-dimensional space, assuming a zero-based origin. And grid allows you to have a non-zero origin, which is useful in very few scenarios, but we have that anyway. What I want to point out here is that n can be any number. So of course, you can work with single-dimensional, two-dimensional, three-dimensional, but you can work with 9 dimensions. If you're a string theorist, maybe that's the kind of data that you have. We let you do that. So n can be any number at all. So let's look at an example to make this more concrete. So let's look at the single-dimensional example. So what I have is an extent. And for those of you from .NET, templates are being used here. It's just like generics, except you can actually pass numbers in, which is kind of sweet. So we say here extent 1, which means I'm going to define a single-dimensional space. The variable is e. I construct it, and I say 6. So I want to have 6 units in a single-dimensional space. And that's not a container. That just defines the shape. If I had the container of that extent, and I wanted to index into it and go to the third element, I would create an index of 1. And I would say, I, name it I, and say 2. And that will point to the third element, just like the graphic shows. If we move over to the middle, in the two-dimensional case, so I would say extent 2 this time, which means the constructor expects 2 integers. And I go and give it and say it's going to be 3 rows by 4 columns. So we're row major, just like C++ is. And then you go and use an index of 2 to index in that space. And you could go to the first row, third element by saying 0, 2. And I'm not going to spell out the third example. Again, it's the same thing. So the most significant dimension comes first. If I wanted to use, if I was working with an API that expected the grid instead of an extent, it's very easy. How do I get a grid from extent? I just go and create it like this. So grid, give the same dimension as my extent, g, and then just pass in the extent, and I'm good to go. Is that fairly simple? It is, right? This is where you nod. That's the interactive part, but non-audio. So you can notice that this has nothing to do with a GPU. This is just some types that you could use anywhere to express multidimensional constructs. So where would they use this? So we have a type called array. This is not what I was using in the example earlier. So array is a container of data which you use to allocate stuff on the accelerator, so on the GPU. So the way this works is it's an array of elements t, so you could say array int, comma, and then you say the rank of the array. So you could say 2 to have a two-dimensional situation. So let's look at the code example I have here to make this more concrete. So let's say I have a vector of integers. So it's got 96 elements, but really how I think of that data is that it's two-dimensional. I just couldn't express it before. So I'll go here and create an extent, and I'll say 2, two-dimensional, and I'll say it's 8 rows with 12 columns, so 8 times 12, that'll give you the number. And then I'll go and say I want an array of integers. It's going to be a two-dimensional array. And then what I'm going to pass into that is the extent. And I could stop right here. At that point, what I would have done is I would have allocated this space on the GPU, ready to receive data. But I've gone further in this example, and I'm actually initializing it with data. So I go and use the iterators on my vector, and I could have taken just a slice of the vector. I don't have to take the whole thing. Here I'm taking the whole thing, and I'm initializing the array, which means at this point, synchronously, you're copying the data to the GPU. There's a way to do it asynchronously as well. So later on, you're going to have a parallel for each. You're going to have a lambda. And then in that lambda, let's say you had an index, a two-dimensional index, which was 3, 9. So it was pointing to the colored square over here. Then you could use that index we have the subscript operator on the array. You'd pass it in, and that's how you'd access the element either to read from it or to write from it. And we also have, in addition to the subscript operator, you can use a function operator, just passing in the raw integers, and you can pass any integers. You don't need to have an index. You don't need to have an index object at that point. So that is array. We also have array view, and that's the thing I was using earlier. An array view is not a container of data. An array view is a view, a wrapper over a container of data. And it's a wrapper over a container of data regardless of where that data lives. So you could create a wrapper of an array, which means now you have a wrapper to the data on the GPU, or you could create a wrapper to a vector or a pointer or anything that you have on the CPU. So how would you use this? Again, let's look at the example here. So if I had a vector of 10 elements, but really I was thinking about it in a two-dimensional way, I create an extent, say it's two-dimensional, 2 rows, 5 columns, and then I go create the array view. I say I want an array view of integers, two-dimensional, A, passing the extent. I have to say what data it wraps, so I couldn't stop here like I could with the array. So I give it the vector, and now I have essentially like an alias to that vector. Right? So there's no copiness taking place here. Now nothing has happened. This is like a smart pointer, if you like. It's an alias for that vector. Then later on, when I go and capture it into my Lambda, at that point, you get an on-demand implicit copy taken care for you. And I want you to notice here, and this is true both for the array and the array view, they have very congruent interfaces, so you can use these things. Once you know how to use one, you can use the other. I could have just said an array view of integers, two-dimensional, and given the extent right here as part of the constructor. So what happens is the extent gets created for you under the covers. And in most cases, you don't have to deal with extents directly. Our APIs let you just pass the raw data in if that is what you want to do. So that's array and array view. And if you go and compare them, you see they have many similarities. I'm not going to read them out. You can do that yourselves. The one I want to focus on, which I've already covered really, is that one is a container for data. The other is a wrapper for data. With the array, you go and do explicit copies, and you have to know about exactly when it's happening and deal with that. With the array view, they're implicit, on-demand copies. OK. Now for the entry point, parallel for each. So parallel for each starts here on line 1 and ends on the second occurrence of line 1. And it takes two arguments, the argument on line 2, the argument on line 3. The argument on line 2 is a grid. And you know about grids now. We just create them with extent. So really what it takes is an extent. So you create that extent. So when you create that extent and you give it to it, you're saying the number of threads that you want to execute the other argument, which is the lambda. And you don't just say the number. It's not like I want just 100. You say how you want those threads to be configured. So really what you can think of extent in this context, in the parallel for each, as that it's a generator of indices. That's the way to think about it. So you're doing a parallel for each on a generator of indices that I'm going to receive into my lambda. Because when you know the extent that you're passing there to parallel for each, you know exactly what indices are going to call your code, what I've named their kernel code. So it's a generator of indices. It's a generator of threads with those indices that's going to execute your code. And then the other argument is the lambda. Now, there's been so many C++ sessions at this conference that I think even those of you not familiar with lambda should know them by now. But let me check. How many people are comfortable with lambdas? Can I have a show of hands? That is not everybody. So the crash course introduction is very, very simple. Is that as soon as you see these funny square brackets where you wouldn't expect them, you've got a lambda. And then straight after that comes a signature. So it's basically a function here. So I've got the signature. So I'm saying, look, this is a function. It's going to take an index. And then I have my braces, and it's the code. So I'm passing code as an argument. Now, within those brackets there, that's the capture list. So that's where you can list the variables that you want to also pass into the lambda that are available above the lambda. So before line 1, if I had any variables like the array view, or the array in our case, you just list them there in the capture list, comma separated, and you can then use them into the body. But there's a convenience. You just say equals, and it means capture everything by value. Or you can say ampersand is captured by reference. So array view and everything else you capture by value. The only exception is array. That's the one you capture by reference in C++ AMP. So that's like a crash course on the lambda and also how you capture the stuff. So there was a question earlier about whether this was synchronous or asynchronous. Before I get to that, let's talk a bit about what happens under the covers here. And I don't have to share this with you, but I like you guys, so I think I'm going to share it with you. So this is roughly what happens at this point. when we compile this, we actually go and look at your code, and we generate for that code HLSL, which is the high-level shader language, which is the language that you'd have to use if we were using direct compute, which is a subset of the DirectX API if you want to work with a GPU. So we generate this HLSL, and then at compile time, we use the HLSL compiler to generate HLSL bytecode. We then take that bytecode, which is really compact, tight bytecode, and we stick it in the binary itself, into the exit, for example. Then what we do is we generate our own method, __kernel_stub. And in that method, we go and do all the DirectX API calls so you don't have to. And we set up the GPU and point to the bytecode that we had in the exe in order to go and execute it on the hardware. So then when you take your binary and you give it to your customer and they put it on their machine, they run the executable app. It comes up. It reaches this point, calls our method that you never see. It's under the covers. It sets up the DirectX pipeline, gets the HLSL bytecode, fires it to there, and DirectX takes over. What happens afterwards is DirectX will actually talk to the driver that you have on that machine. That's why you need a DX11 driver. And that driver is going to be from a hardware vendor. So it takes the HLSL bytecode that is already tight and optimized, but goes and actually converts it to its own format that it understands. And that's how we get this great hardware portability, even at the same time from the single binary. So that's roughly what happens under the covers at this point. So obviously, when you go and do something like that where you're going to hand stuff off to other hardware, this is asynchronous by nature. So after line 1, any CPU code you have, that's just going to continue executing, and it doesn't mean your kernel has completed. So that is an asynchronous situation that we have here. However, at any point where you try to observe the side effects of that asynchronous operation, and what does that mean? It means any point you try and use the data that you're expecting to be modified in the lambda that you pass to the parallel for each, we will synchronize at that point. So we will block at that point, wait for the kernel to complete if it hasn't, and then copy the data back. So you have to be mindful of that. If you want to do other operations, you can do other CPU operations, and there's a way for you to check, is the data ready? You can do an asynchronous copy, basically, and get a future back, and then you can be notified on that when the data is ready so you can go and use it. So you're in control as to how synchronous you want to make this or not. So that's why we say it is as if synchronous in terms of visible side effects. You're not going to shoot yourself in the foot from a correctness perspective, but it's really asynchronous in nature. Does that make sense? Yes?
In the case of the copy arrays example, then would the destructors for the array view objects then perform the synchronization?
The question was, so in the array view example, not the array, so in the array view example, when the code exits, how do I get the data back to my original source? And you're absolutely right. In the destructor, we call a synchronize method on the array view, which is what causes it to go back to the original data. So just to elaborate on that a bit more, so when you use the array view, you can continue using the array view after you called parallel for each, and you should access the data through that. But if you wanted to then access it through the original data, you have to call synchronize yourself, and we call that in the destructor. I would suggest you call synchronize yourself, because then you have a chance to catch any exceptions that may occur at that point, whereas in the destructor, they'd be lost. OK. So the only thing I didn't touch here on was the thing in green. And for those of you that are colorblind, the restrict direct 3D part, that I didn't touch on that. And that's the key new language feature we're adding. If we didn't have that, you could go in your Lambda and make, for example, system calls, which obviously are not going to work when you offload this thing to the GPU. And then you'd be dealing with runtime issues. Instead, we check everything at compile time, which means when you write your code, after you build it, if it compiles, you're good. You're not doing anything illegal in there. And that's why we have restrict direct 3D. So let me talk a bit more about this. So the restrict part is the restrict modifier. And this is the language addition. This applies to functions, including lambdas. And you can put that on the function or lambda to signify that you want to do something special about this. You want the compiler to do something special about this. Check something or generate some extra code for it or whatever you like. So it's a generic feature. It's not tied to C++ AMP. However, in this first release, it is used only by C++ AMP and can only be used by C++ AMP. So what comes after the restrict in the parentheses, without quotes, is the restriction specifier. And there's only 2 specifiers that we have offered, and only the compiler vendor can add other specifiers. And the 2 specifiers we're offering is CPU. So you can say restrict CPU, and that's like a no-op. That's like leaving it blank. All your code today is restrict CPU already. And then the other thing you can do is you can say restrict direct 3D, and that is a single new addition. And you can combine them as well. So what are the restrictions? There's quite a few, and you can read them. I'll let you read them. I'm not going to go through them. I trust in your ability to read most of the time. So the restrictions, you may be wondering, where do they come from? So the restrictions are of the underlying direct 3D platform that we build on. And why are they in there? Because of the restrictions that are actually on the GPU. So as we'll see the GPUs relaxing the restrictions, we'll see Direct3D relaxing its restrictions. And sometimes we can relax a restriction even though Direct3D doesn't, but I'm not going to go into that. And then you'll see that this restrict will become less restrictive in the future. And we do have a versioning story in mind. I'm not going to elaborate here. I've blogged about that. There is a way that we'll be able to deal with versioning of restrictions in the future. There's more restrictions. It's not just these, although I have to call out, I'm saying that lambdas cannot capture by reference. The single exception to that is arrays, of course. And here's more. So essentially, when you look at all these restrictions, it goes back what I said at the very beginning. You can think of the GPU as a number cruncher. Really large amounts of data, potentially multidimensional, where I want to do math on it, you just offload it to the GPU. It's not even math, it's arithmetic, technically. So those are the restrictions. Here's an example which actually preempts the question, why did you have to use a restrict? Why didn't you use mechanism X instead? What we thought was very important is to have restrict truly be part of the signature of the function. So that allows us to do things like overloading, which we thought was really important. And that's what you're seeing in this example over here. What this means is you can actually have code which, if you think works on both the CPU and the GPU, you can just annotate it with a strict Direct3D, comma CPU. You can distinguish that. You can have a Direct3D only version, a CPU only version, just different by the restriction, and it makes your code much cleaner. So we thought overloading was very important, and that was one of the main drivers in us introducing restrict rather than using some other mechanism. So that's restrict. Now you've seen all these elements in more depth. Let's revisit it with another example, this time a matrix multiplication. So in this example here, what we have is the serial code on one side and the one that uses AMP on the other. You know the trick by now. In this time, I'm using vectors. So I want to take these. I want to take the so vector A and B are the ones I'm going to multiply, so the matrices, really. And are you familiar with matrix multiplication? It's very simple. You basically take each row from one and each column from the other, and you multiply each element, keeping a sum, so adding, and in the end, you have a single result, and you store that in the resulting array. You can go on Wikipedia and look at matrix multiplication if you're not familiar with it. The point here is that look at the algorithm. So the algorithm stays the same. So I take my vectors, wrap them into array views, and I'm thinking of this as two-dimensional. I said it's matrices. They're floats in this instance. I'm using this const, which means, hey, don't copy this out in the end. This is only to be copied in. So it's an optimization indication. And then I have another mechanism for C, which just basically says, do not copy this in. I'm only interested in copying this out. So there's tweaks like that all around. And then I go and I want to pass the extend, so we know how grid represents an extend. And I want to have a thread for every single element in my output data. And that's a very typical pattern, so we made it very easy. You just go to the array view C and say, hey, give me your extend or your grid in this example. Then in the actual Lambda itself, I go and take the two components of the index and just store them in variables that have the meaning that I know for my algorithm. And again, I think you'll be using this quite a bit yourselves. And then when you look at the bolded part, the algorithm, it's exactly the same, except the one in AMP is nicer, because it doesn't have that funny arithmetic that you have to do with the index to cope with a situation where you really have two-dimensional data, but you're storing it in a flat manner. What do you mean by that exactly?
As in, the GL can handle vectors and has it not product?
Oh, I think, so the question, I think, is related to vector types, as they're known in HLSL. In the bits you have today, you don't have that, but there will be a beta, and thanks for your feedback. So that tells you, that gives you now a better feel about what you saw earlier and where we are now. There should be a question. I can feel someone has the question, but I'm going to ask it for you, which is, you've been talking about using the GPU, and nowhere here have I specified the GPU. So what happens if I have two, for example? Or how can I check the capabilities of a GPU? Maybe I don't want to run on it. how do you do that? So you guys should have asked that, really. So I'm going to assume you did. And it's funny you should ask that. We have this other types, which is the accelerator and accelerator view. So an accelerator represents a parallel device in your system that C++ AMP can work with. An accelerator view is just a view on the accelerator, and you can think of it as a queue. And actually, accelerator view is what you'll be using most of the time. So what this lets you do is it lets you, and the graphical example on the slide is for a GPU, it doesn't have to be, for a discrete GPU, in fact. So what you can do is you can check, before you do any of your operations, what are the capabilities of this GPU? Does it have double support? Because not all GPUs have. And maybe if it doesn't, you want to implement a CPU solution, right? So you can check stuff like that. Or, like in my demo earlier, when I use the 2 GPUs, you can actually get an accelerator view, and you can, using code like this, you can actually say, hey, this parallel for each, execute on that GPU. This one here, execute it on this other one. And it's down to you to actually split your data and synchronize and do all that kind of stuff. And we'll have samples that show you how to do it. So you can go and create an accelerator directly, if you can remember the really, really long strings that you get for the Windows device ID. Or the more common thing, you can enumerate all the accelerators in the system and go through them and check capabilities, choose, do whatever you want. That includes an emulator accelerator that we actually ship. A really, really slow accelerator is the ref emulator, which is only useful for debugging, really. It also includes a fallback accelerator, which actually is not very slow, although it's slower than the GPU, obviously, which allows you to take advantage of SSC, so it will execute using SSC and multi-core on the CPU. So we think of that as not a primary target, as a fallback solution. So if you happen to have your code running somewhere where there's not a DX11 card and you don't want to roll your own CPU implementation, you can fall back to that. So that's just a bit of stuff on accelerator and accelerator view. They enable other scenarios as well, but in this introductory talk, I'm not going to go through that. So at this point, you know most of the C++ AMP API. What do you think of it? You like it? OK, so now we can make things go a bit hairier. So we have other constructs, 4 other concepts that I want to introduce to you. And they complicate things a bit. They build on everything that you know so far. The advantage is you can actually dial the performance up to a different level. So if you can get 80x, 80 times faster serial code with what I've shown you so far, maybe you'll get 150 times with using the technique I'm going to show next. And I could do a whole session on this, but I'm going to go very quickly through it just to give you an overview. So bear that in mind. You're not going to understand all of this by the end of it, but you'll have an understanding enough to go and read more about it later. So when we went and scheduled our threads, we're using the extend. So in this example, I'm saying 8 by 6. This is how you can think of your threads. Each cell is a thread. But you can actually tile this. What does that mean? Let me show you an example. That's the best way to understand it. You can go on the grid where you pass the extend, and you can say tile, and then you can give, in chevrons, you can say 4,3. So what that is saying is, yes, schedule all those threads, but schedule them in such a way that I'm going to get tiles of threads where each tile is 4 by 3. So each tile has 12 threads in it in that configuration. So how many tiles do I get when I say 4 by 3? Well, 4 by 3 is 12. The original one had 48, so I get 4 tiles. And those 4 tiles are 2 by 2, as I'm showing with the bolding up here. Let's see if you got this. So if I say tile 2 by 2, I'm saying I want tiles which are 2 by 2. So each tile is 4 threads. How many tiles am I going to have? 12. I can hear you. You be brave. That's good. 12. And if we go and look at that configuration, it would look like this. So it's 4 by 3 in this example. So that's how you tile. You still don't know why you would do that, but that's how you tile your threads. So what do you do when you tile? You get back a tiled grid, and we have another overload of parallel for each that takes a tiled grid. And as soon as you give a tiled grid to a parallel for each, it's going to give you in the lambda a tiled index. And you can only use this technique for up to 3 dimensions. So the string theorist has to stick to the other approach. So if you have up to 3 dimensions, 1, 2, or 3, you can use this technique. So OK, I've got tiling. I get this tiled index. How is that different? Well, let's look at an example. So in this example here, I've got the array view, which is 2-dimensional of vintages. So I've given the extent here implicitly. I'm saying 8 by 6, parallel for each grid. And then I go and say tile 2 by 2. So this is the example we saw earlier. And then I get a tiled index. And if that index, let's say at runtime when it's executing my kernel, was this thread here, then if I go on the tiled index and I say global, I get the global index, the one we know already, which is going to be 6,3. Right? That makes sense. That's the index you already know. But in addition, I can get other indices. So I can go local and get the local index of that thread within its own tile. I can say tile, and that will give me the index of the tile itself in relation to all the other tiles. And I can say tile index tile origin, which will give me the global thread ID of the local ID 00 within that tile. So I can use a whole bunch of other indices. I think this is straightforward. You still have no idea why you would do this, but that's straightforward in terms of using it. So here's why you would do it. As soon as you use tiling, now in your Lambda, you can actually declare variables as tile static. And when you declare a variable as tile static, all threads in the tile share that, so they get the same value for that, and they can access that type of memory, the tile static memory, much, much faster, let's say 10 times faster than what they were able to access non-tile static memory. So when you're using the array or array view, that goes to the global memory of a discrete GPU. And accessing that, let's say you access that and you can get 10 gigabytes per second. Using the tile static, you get 100. So what you would do with a tile static typically is copy a tile size worth of data from global to the tile static, and then do your algorithm on that when you do the continuous accesses, and that's how you get the performance improvement. Now, when you do that technique, you need to synchronize all the threads in your tile. Because while they're copying stuff down, you don't want one of them to just keep going further and now run the algorithm on memory that hasn't been initialized. So for that reason, from the tiled index, you can get a tiled barrier, which is the simplest class you'll ever see. You can't even construct it yourself. So you get the barrier, and then the only thing you can do is call wait, and that will synchronize. So all of threads in tile must reach that point before they continue. Like I said, this is like a very fast introduction into it, and here's some very simple code to demonstrate it. Yeah, laughter was the reaction I was expecting. So on the one side, I have the matrix multiplication I showed you earlier. And on the other side, with red, I have annotated the introductions and changes I had to do to use tiling. So what you can see here, I'm just going to go through the pattern. I'm not expecting you to understand all this. You'll get the slides. You can study it on your own. And I have a blog post explaining it in more detail. So first, I decide my tile size. So I'm saying 16. So 16 by 16, I'm going to get 256 threads in a tile. And then here, I'm going to go and take the local indices from the thread ID, and I'm going to use that row and column variables later on in my algorithm, which is the same as I had over there. And then I go in a loop for every tile, and here's my tile static. This is typically what you use for tile static. So you use these arrays, log A and log B, which I actually initialize with data from the global array. So you still have to go to the global memory once, at least, to copy the stuff down. So I copy down tile size worth here. That's what this arithmetic is doing. Synchronize, so we get all the stuff in. And then you look at the algorithm. If you squint, it's exactly the same. Instead of working on the global arrays, I'm working on my tile static local ones, and I do that for each tile size only instead of for the whole thing. A barrier afterwards to make sure that we're done at this point. Then we loop around. And in the end, I can go and use the global index to write to the output array. So that's kind of the same pattern for most algorithms. Not all, but for most algorithms, it's kind of a pattern that you can use when you use tile static. And why would you do this? Because you're not happy with your 80x or 50x, and you want to get even more. You're greedy, and you pay for that with complexity by doubling the size of your kernel. So at this point, you now truly have seen the entire core API that we have, which is all the stuff that you saw previously, and a very, very rapid introduction overview into our tile static. That is another language addition. You can only use tile static within restrict direct3D functions, and only when you're using a tiled parallel for each. And then the tiled grid, which is the same as the grid, but tiled, a tiled index, which is the same as the index, but you get more from it, and the tile barrier class. And that what gives you the speed limit infinity, which I really like that because it looks like the Visual Studio logo as well. So, and it's got a cloud behind it. I mean, how much better can it get? I should copyright that image. I created it. OK, so that was tiling. And you can ask me questions about that later on. How are we doing on time? We're good. The stuff I didn't cover. So that's the core API, but we have some other things as well. And I didn't cover them, so I won't. I just want you to be aware of them. If you're interested in that, come and talk to me. And that concludes what I said at the beginning would be the largest section of the session, and indeed it was. So now we can move over to the Visual Studio IDE. I think I may be able to take one question, so you've got it.
What languages can you drop code in?
the interrupt, so you saw the bullet on the previous slide. So you're asking me about the stuff I'm not covering already. But so the interrupt had to do with DirectX. And you've seen a lot of DirectX sessions here. So if you're actually using DirectX like I was doing in my N-body example, you don't want to have to use a compute kernel to calculate where all the particles are going to be and then copy that data back to the CPU, only to copy it to the GPU again for your pixel shader to go and render it. So we have interrupt APIs where you can just leave the stuff resident on the GPU to be used by other HLSL kernels. So that's what the DX interrupt is primarily about. And also with the accelerator, you can interrupt by getting a device context. It is native C++ code, but the interrupt would go to other C++ code that would be using HLSL, for example. Yeah. And on the interrupt, I thought what you were going to ask when you said interrupt, and I'm sure someone is thinking about it. This is not available directly in C# or JavaScript, but obviously you can interrupt with C++, right? C++, and then use that from your .NET or JavaScript code, like you've seen so many examples. And all of this works in Metro-style apps as well as on the desktop. So Visual Studio. Visual Studio is a very powerful tool. I love it. And we have full support for C++ AMP in there, as you would expect. In your bits today, you already have C++ AMP. It's with Visual Studio Express, and any other SKU, you get C++ AMP. And I'm not going to go through everything that we've done in Visual Studio. The thing I want to focus on is not even this, but since it came up, the concurrency visualizer, which is a performance tool we introduced in VS 2010. It also supports GPU profiling at the DirectX level, and we're working on a C++ AMP higher level integration, which you're seeing on the screenshot, but is not in the bits that you have today. So I just wanted to give you a heads up on that. In addition to that, we've done a lot of work in parallel debugging. So when I explained earlier the parallel for each and what it does under the covers, you can imagine how do you get source debugging for that? You need magic. Or a whole bunch of people to throw it for a whole bunch of time. And that's what I want to go and show you, actually. So let's see, which machine is this? So we click there, and then click here. This is very simple. Windows security in action again. All right. So which one shall I use? I'll use that. So here, I have a C++ project. And it has a single code file in it, moth.cpp. So I've already inserted a bug in there. That was a joke. There's no other bugs in this code. And in fact, it doesn't matter what the code does. All that matters is the debugging support that I'm going to show you. So what you need to know is that from main, we call matmul amp, setting up the data that it needs. And it's going to go and do a matrix multiplication. And what I'm doing from matmult is I'm calling doit. From within the parallel, the lambda that I pass to the parallel for each. So doit must have restrict direct3D on it as well, and indeed it does. My parallel for each here is tiled, so I'm using the tile sizes of 16. So 16 by 16, I'm going to have 256 threads in there. And what I'm doing is I'm calling doit, and then in the end I'm going to write the results. Again, it doesn't matter what the code does actually. All that matters is I've put a breakpoint. So the question is, can I hit that breakpoint? That's the big question. And it took us a lot of time. But yes, you can. We can actually hit the breakpoint in the C++ AMP code. I'm very proud of that. Beyond breaking, I can step. So I hit step, boom, I've stepped to the other line. I can go here and look at the variables. So I can inspect the variables here. I can look at my locals window. It finds all the locals, shows me the values for that. The autos window finds all the expressions around the line, show me the lines for that. Watch window, I can go and add watch expressions. So I can go here and add watch for some. I can go and select the actual expression here, add watch for that, and you can see the values as you would expect. I'm on this line, so when I step, what's going to happen? Sum is going to go into this other expression. So as you would expect, when I go and step, indeed it goes in there. You can see it in the watch window. It's red to show that it changed from previously. So all the debugger features that you know are actually working there. You have the call stack window. So in the call stack window, here's the kernel stub I was telling you about earlier. You, of course, can see that in the debugger. And then from kernel stub, it calls your user code, your lambda, which is represented by this stack frame over here. So this call stack and the locals and everything, of course, belong to a single thread. That's the way it works, right? So what thread is executing my code right now? Well, if I go up to the top on the debug location toolbar, I can see that. So I can see here it's the local index 00 on the tile 00. So I can see exactly which thread is executing this code. Now, this thread has reached about the end of this kernel at this point, but others will be in doit or will go there. So let me go in doit and actually put a breakpoint on the last line. So we'll put a breakpoint right here. And then if I go and continue, you can see that now the call stack has changed. The locals have changed. We're actually now on thread 04 in tile 00. And of course, I have a call stack, so I can go and double-click here, and that'll take me to the other stack frame. So you can see a call stack here. We're preserving your illusion that there is a call stack on the GPU when everything actually gets inlined into HLSL. So you get to debug at the abstraction that you actually coded. And I want to draw your attention, if you look in the code gutter or the editor margin, as it's called, I've turned on this feature, thread markers, and we've made that much, much more useful both for CPU and GPU code. So you see here the thread marker, it's telling you there's threads there. And when you hover over it, look, it's telling you there's 4 GPU threads and their status. They have completed. They're done. But if you want to look at GPU threads, you don't have to go to the code margin. You can go to the GPU threads window, which, did I tell you these were preview bits? OK, so let's try that again. So the GPU threads window, I had it open. In case you want to know where it is, you go to the debug menu, Windows, and then you go and open it. And then it doesn't work still. So let me try stopping and starting that again. I'm glad this is recorded, because the developer would say, hey, it doesn't rep on my machine. So here you can actually see the threads window. This is good, because I get to show you more stuff, actually. So you can see here I have 4 threads that are active, and I have 252 that are actually blocked. Because they're actually, where are they? Let's go and find out. So I double click, they're in a tile barrier, I go back on the call stack, they're now in do it. So when they're in the barrier, we show that they're blocked, so you can actually see the state of your thread. If you have divergence, which is a topic I haven't covered, we'll show you that as well here in the debugger. So instead of actually using, let's put another breakpoint down here. We have one. So let me have 5 to continue. Instead of using the call stack window to switch to stuff, you can also use the parallel stacks window. So if I go and open the parallel stacks window that we introduced in VS 2010, you'll actually see that this is telling you, hey, you've got 256 threads. They started from kernel stub and lambda, and 252 of them went to do it and are actually in the barrier wait. So you get a global picture of where your threads are. And as you go and hover over these things, you get, again, the tooltips. And these are rich interactive tooltips, so you can go and switch threads from here, right-click, do stuff to them. We're really using WPF to its fullest. So if I go here on the active threads, I could go and switch within these 4 that are on line 33. So I can go and select here in the thread switcher. And let's look at the value. What value do we have for some here? 273 something. Let's see if I switch to 1. 27. So this is a different number, 3024. Let's switch to another one. 2. Yeah, so you can see that actually these variables obviously belong to a stack frame of a thread. So if I want to see the different values for different threads, I have to switch to specific threads. Now, what you don't want to do, whether you're doing GPU data parallel code or whether you're using CPU data parallel code, you have to switch to every single thread to see the value of a variable on every single thread. That is a terrible situation. And of course, I wouldn't be raising that as a question if I didn't have an answer. So the answer that we have is the parallel watch window. So let me delete that I added earlier. So here in the parallel watch window, I can actually see the threads in a raw list. So I can actually switch now directly without using the thread switcher. And I see the threads that are in a specific method. So here, for example, in this case, in doit. And what I can do here is I can go and add to parallel watch. And then I can go and actually look at the sum variable across all those different threads. So it's giving me an error indication, which means that these variables, they don't have a value because they haven't reached that point yet. So this is going to be incredibly useful for debugging data parallel code, both on CPU and GPU, because you can sort on this. You can group by these columns. You can add other variables and compare different variables across many different threads. You can go and export to Excel and go and do analysis there if you want. You can filter within this window directly. In fact, on the filtering front, I could just flag threads, and let's say I want to focus on just these 3. And then my entire UI, I can narrow it down to exactly the set of threads that I want to be focusing on. There's a lot more features in the parallel debugger. There is freezing of threads, so you can just keep them exactly where you want, so you become the scheduler, and you can continue others. You can run whole tiles to exactly the place where you want. It's really a rich experience. It's richer than what we had in CPU, because we've added so many parallel debugging features for the CPU as well in VS 11. So that's all I have time to show on the debugging front. You guys like that? So basically, everything that you know about CPU debugging in the great Visual Studio works for GPU plus more. I'm not going to talk about the concurrency visualizer. You saw a screenshot earlier. But yeah, play with that in the bits you have, and there's more to come in that area in the beta, whenever that is. And that concludes the IDE section. So now we're left with a summary where I'm going to quickly summarize and give you some important pointers for more information, and then you can go and get the printed chapters that Kate has over there. So in summary, what I've shown you today, I hope, is that by allowing you to very easily from C++, from your mainstream language with the same compiler that you have today, to tap into the power of hardware such as the GPU, we're really bringing performance to the mainstream. And we're doing that in C++ with minimal API and language additions within the market-leading, award-winning Visual Studio with the rich debugging support that you saw there. So we are doing all this, bringing performance to the mainstream without sacrificing at all your productivity. And we do that building on a hardware abstraction platform that doesn't compromise at all your portability. You saw the demo at the beginning. Again, nobody can do that kind of portability that I demonstrated there, running on both NVIDIA and AMD cards at the same time from the same binary. And this protection of your investment from a portability, hardware portability perspective goes into the future as well. So you've seen the API. It is not a GPU API. It's a data parallel API. It's an API that actually is future-proof in its design for hardware that we've yet to see. And as the last bullet says over there, we don't want to keep this just to ourselves. So we're already working with other compiler vendors to have C++ AMP implemented in other compilers, even on other platforms. Our goal is to basically bring this kind of power to the mainstream, and that is the only goal without any strings attached. So I hope you enjoyed what you saw here. You please do fill in the session feedback. It's very important to me. So I'd like to read your comments there and see what you thought of it. If you have questions, which I'm sure you do, we have an MSDN forum, and we also have the Dev Center for Parallel Computing and the blog. All those three are shared with the Parallel Patterns Library team. So we're the same team. So all your parallelism needs on the multi-core CPU, a GPU cluster, whatever, you can go to those three links. And at the top, I've put my blog where I've already been blogging about C++ AMP. And there's an email button there. You can just hit on it, and you can contact me directly. So again, thank you very much for turning up. Don't forget to pick up your chapters.